Materials Project 2, made by Alex, Cole, and Stewart.
So firstly, if we want to find our interatomic distances between two atoms, we should take a look at our Lennard-Jones potential energy equation, which takes the form of interatomic potential energy equals some repulsive constant, let's just say AR, over some distance between atoms, let's just say R, and that's the 12th, minus some attractive energy constant, we'll call BA, over R to the 6th. And if we plot both of these separately on an energy graph by the distance, so we have U and R here, we can see that the repulsive energy starts out very, very high and takes a sharp decline directly towards 0. It never actually reaches 0, but it just keeps kind of going on here for infinity. And our attractive energy starts lower, but also takes a much shallower line towards 0, but eventually, again, almost 0 until infinity. If we then combine these into one total energy function, as we see up here in the Lennard-Jones equation, we will get a better understanding for what's actually happening here, as the repulsive energy overpowers at very, very low interatomic distances. But once you hit a certain threshold, they start to even out a bit, and then the attractive energy starts to pull back, and they again start going towards 0 and go towards infinity. Now, for interatomic distances, we want to look at this point right here. And this is based off of the knowledge that the universe is always trying to drift towards some low energy state. So the atoms always want to kind of go towards this valley or minimum spot. And since this is a minimum, we can take the tangent and see that it's actually parallel with our x-axis. And since this is the case, if we take the derivative of this function, which in case is the derivative of our Lennard-Jones equation, and graph it, we will actually find a graph looking something like this as you go along R. Now, what actually is this graph? Well, first, let's just think about it logically here. As you're before this point, the repulsive energy is pushing you away. And when you're after this point, the attractive energy is pulling you closer. This point is simply just the point at which those forces cancel each other out, and you have a net force of 0. So this is actually just our force equation. And this equals 0 when our interatomic distances are at equilibrium. One thing we also have to think about is that there will also be other solutions to this equation of force. Due to the fact that our R values are such high quantities, there should be around 6 solutions. However, we're only looking for the one solution. How do we know which one we want to find? Well, due to the fact that this curve never actually reaches 0 past this point, we can assume that all of the other values here that are solutions are simply just imaginary. They don't exist. And also that this graph is actually going to be mirrored on the y-axis, so it will have negative components as well. So we have two imaginary components in the positive, and then a negative component and two negative imaginary components. So I've written up a little bit of code to kind of model this. And firstly, you set your R as a variable, and then insert your energy equations. And then we can differentiate our energy equation and solve that as it goes to 0 in terms of R. And then after that, we need to sort it to get rid of all of the imaginary numbers. And then we need to find the minimum for all positive numbers. And once you do that, I'll run this real quick. And this is going to be our long equation for our aluminum equilibrium, and that simplifies down to 0.2806 nanometers. And then if we find our iron, there's that long equation. And if I chuck that one in, then we'll get 0.2825 nanometers. And that would be the interatomic distances between iron and aluminum.
Vacancies are a type of point defect in material. Point defects being localized disruptions in a crystalline structure. Vacancies are when an atom in the atomic structure moves from its normal position out of the structure, leaving a hole in the atomic structure. This process usually takes a lot of energy. The energy needed to move one atom out of an atomic structure is called the formation energy. The amount of vacancies in a material varies with temperature. There are always vacancies in materials formed above absolute zero. At absolute zero, there are no vacancies as there is no entropy in the system, which means that there isn't enough energy for the atom to leave the atomic structure. The Arrhenius equation describes the relationship between the rate constant of a chemical reaction and the absolute temperature. It is described as shown, with NPD is the number of points where defects occur, over N, which is the number of total points, which equals E to the formation energy over the Boltzmann's constant times temperature in kelvins. The way to find the total number of points is using the equation on the below, using Avogadro's number times the density of the substance divided by its atomic mass to be plugged into the Arrhenius equation. For this project, we used 298.15 degree Kelvin for the equation for aluminum, which N equals 6.022 times 10 to the 23rd power times 2,700 kilograms per meter cubed over 26.98 U, which the calculation becomes 6.026 to 10 to the 25th power. After finding out the number of points, we're able to find the amount of vacancies per point, which, when you plug it into the equation, brings you to 3.999 times 10 to the 37th power of vacancies per meter cubed. We use the same temperature as we did with the aluminum, at 298.15 degree Kelvin, with the amount of points with 6.022 10 to the 10 to the 23rd power times 7,874 kilograms per meter cubed over 55.84 U, it comes out to 8.492 times 10 to the 25th power. Using the number of points, we're able to find out the amount of vacancies per meter cubed, just like we found out with the aluminum, by plugging it all in, which comes out to 6.431 times 10 to the 54th power.
Vacancies are defects in the material, and generally these defects lower the material's yield strength as they create points of weakness where the material can become more easily dislocated. This, however, can change with temperature. At higher temperatures, more thermal energy is added to the system, which causes the dislocations to move easier, making the yield strength lower. The opposite happens at lower temperatures. There is less thermal energy, so the dislocations don't have as much energy to form as when the temperature was high. This leads to a higher yield strength. Additionally, not only does a higher temperature cause the dislocation to move more freely, but more vacancies form at higher temperatures. This is due to the additional energy in the system providing the formation energy needed for the atom to move out of the atomic structure, leading to a lower yield strength as there is more points of dislocation. Again, the opposite occurs at lower temperature, meaning that at lower temperatures the yield strength is higher.